Okay, this is a sample MINM.M10. And in this, we're basically looking to make a matrix that is invertible. Remember, the inverse of a matrix is such that if I multiply a matrix by its own inverse, I get the identity matrix. But that's not what we're going to exploit to actually figure out what x, y, and z are here. That would be complicated. What's much easier is let's use another property of invertible matrices, and that is for a matrix to be invertible, the vector set that it's comprised of has to be linearly independent. Only a matrix formed from a set of vectors that's linearly independent will actually be invertible. So that's the property I want to exploit because it's pretty easy to find basically a set of vectors, a vector x, y, z that goes with the first two vectors so that the set will be linearly independent, okay? So in order to work this, the first thing I'm going to do is assume values for x and y. Turns out there are lots and lots of vector sets for x, y, and z that will make this linearly independent and therefore invertible. So I'm going to make some assumptions. I just need it to not have the same ratio numbers as the other two vector sets, and that will guarantee that basically these aren't parallel to those planes. So I'm just going to say, let's suppose that x is equal to 0 and that y is equal to 2. And then we're going to find limitations on what z can be after assuming these first two. You could almost assume any ratio between x and y as long as you don't use 1 to 3 or 2 to 0. Okay? Okay, well, here we go. Then let's write the new matrix this would be, which would be 1, 3, 1, 2, 0, 1, and now it's 0, 2, and z. And what do we want to do with this? Well, we want to turn this into a reduced row echelon form. Now, of course, doing that with a variable means I have to do it manually, so I'm going to go ahead and perform the steps for this. I'm going to not show them, but I went through and did this. Again, with technology, it's not really possible to place a variable there and then go through the RF process. But when you do it, this is what you end up with. So RF produces 1, 0, 0 and 0, 1, 0. And then the third column turns out to be 2z, negative z, and negative 6z. And because I have pivot rows in row 1 and 2, it's only row 3 that I'm worried about. This will produce definite solutions other than the trivial solution as long as z isn't 0. If z was equal to 0, then the only solution to the system is 0, and then it's not linearly independent. So what I want is for there to be a definite non-zero solution to the system. So clearly this can't be 0, because if 6z is equal to 0, then that means z is equal to 0, and that means the solution to the system is 0, 0, 0. So that's what I need not to happen in order for this to be linearly independent. So there's lots of choices for z that would make this. It just can't be 0, so negative 6z cannot be equal to 0. So what do I choose? I'm going to choose z equals 1. That's like the easiest thing to choose. So that gives us our x, y, and z. Z is equal to 1. And then that'll make A invertible. Do we need some proof? Sure, let's prove it. So my new matrix A is 1, 3, 1, 2, 0, 1, and now 0, 2, 1. And in order for this to be invertible, I should be able to now find its inverse. And of course, the easiest way to do that is to do the RF of this, where I've replaced the other 3 columns with the identity matrix. So this will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is that technique where turning this into the identity matrix then turns this guy into the inverse of A. So when I do that, when I RF this guy, what I end up with is this. So it's 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so that proves that this was invertible. And the inverse matrix is 1/2, 1/4, and -3/4, 1/2, -1/4, and -1/4, and then finally -1, 1/2, and 3/2. And I'm not going to go through the work to show it right now, but this then is the inverse matrix. That is, this right here is a to the -1. And if I take this matrix, and I multiply it by the matrix that I formed by finding x, y, and z, I will actually get the identity matrix. And I kind of have the proof of that right here. If we RF this extended augmented matrix and we get the identity matrix here, then the matrix that remains in the far half must be the inverse matrix. So that in essence proves that that's what that product will produce. And I'm not going to go through the work right now to show it. So kind of an open-ended question, because this isn't the only solution. Literally, you could choose hundreds, thousands, millions of combinations for x and y, and then all you'd get is a limitation on what z was from the RF matrix. And as long as you don't follow that limitation, then you'll get any other value you can choose.